Step 7, I can create and solve systems of linear equations and inequalities. We've been working with equations for several weeks now. A system of equations is just where we have two scenarios happening simultaneously, and we want to know when they intersect. For instance, in this first example, this is a real scenario. Someone is mowing lawns to earn money. You make money by mowing lawns, but you also have to spend some money. You have to buy gas for your lawnmower. You have to buy the lawnmower that's going to do the mowing. There are costs associated as well as income. So we can explain the cost like this. It costs $450 for the lawnmower plus $8 for every yard. Maybe that's how much gas it costs, $8 in gas. And then you can charge $35 per yard. So that would be our other constraint. When we graph these constraints, these equations, we can then see visually before I break even and start making money. In other words, right here at 4 yards, the cost is greater than the income. You're losing money if you only get to mow 4 yards. But up here, once we get to about 18, notice you're making more money than it costs you, and that's where you start to make a profit. We can solve systems by graphing them like this and seeing where they intersect. We can solve them algebraically with methods like substitution and elimination. And then we're also going to learn one new way in this step called using matrices to solve. You can kind of get an idea of what it would look like to solve graphically. You're just going to graph each line. Most of the time people either use intercepts or they get it into slope-intercept form. Begin with the B, move M, and get the lines graphed. So we kind of have a pretty good understanding of how we would solve with graphing. Substitution you learned in Algebra 1, but it's been a while. So let's take a look at solving this with substitution. Just like the name suggests, when you substitute, you take one thing out and put in a replacement. Like a substitute teacher, your teacher is removed and a replacement is put in as a substitute. I like to make a t-table when I do these. I think it's easier to keep track of my equations. So I'm going to put the first equation on my left. And I'm going to put my next equation on the right. Now, we have two variables in this equation and two variables in this equation. Our goal is to find a variable that can be easily isolated. Of those four, this variable is the easiest to isolate because all we have to do is subtract 6x from both sides. And we have y equals negative 6x minus 21. Y is by itself, so we take everything that y equals and we put it into the other equation for y. Now we could have solved for any of these four variables. I just chose the one that didn't have a coefficient. Well, it has a coefficient, it's 1, but that's the easiest one to solve for. So now I'm going to rewrite this equation, 3x plus 8y, but I'm going to take out y and put in some parentheses. And then in those parentheses, I'm going to write what y equals from my right column. Now I distribute. And I solve. I have like terms here that can go together. I can add 168 to both sides. That gives me 204. And then I can divide by negative 51, get x equals negative 4. Now we're going to take this and put it back into the other equation for x. We're substituting again. Negative 6x minus 21. When I put a negative 4 in for x, y equals 24 minus 21, so y equals 3. This literally means that if I were to graph these two lines, they would intersect at the point negative 4, 3. And if I substitute these points into the equation, 12 plus 24 equals 36. Negative 24, that's negative 4 times 6, plus 3 equals negative 21. So I know my solution is correct. The elimination method is the next thing we'll talk about briefly, because these are not how we're going to focus on solving our systems in Algebra 2. This is kind of how we solved them in Algebra 1. Elimination method, we want to eliminate a variable. So we have our x variables, we have our y variables, our y terms, and we have constant terms. And we want to eliminate either the x's or the y's. Neither the x coefficients are opposites or the y's, so I have a choice. I need to do something to make them opposite, so I'm going to leave the second equation just how it is. My first equation, however, I'm going to double it. I'm going to have negative 6x plus 16y equals 72 because I doubled every number. Now you can see that the x's are going to cancel. The y's give me 17y, and the numbers give me 51. Dividing by 17, y equals 3. It's easy to solve an equation with one variable. The problem is we couldn't solve it when we had two. So now we know what y equals, so I just go back to my original equation, take your choice, either the second or the first. I'm just grabbing the second one because it's so close here. Plus y equals negative 21. I'm going to substitute what y equals and solve. 6x equals negative 24, so x equals negative 4. We get the same answer using the elimination method as we did when we used the substitution method. We're not going to take the time to graph it because, again, I think you understand that all we'd have to do is to get y by itself by adding 3x to both sides and dividing by 8. And then we'd do the same with the second equation. And we'd graph them both and find where they intersect. They would intersect at negative 4, 3, both of these lines. So let's talk a little bit about some vocabulary next. We want to know what these terms consistent and inconsistent mean. Literally, a system can be described as consistent or inconsistent based on if they have a solution or not, or if the lines intersect when they're graphed. If they do, the system is said to be consistent. If they do not, the system is inconsistent. And the way I like to think of this is if you have two small children that got into trouble and you ask each one what happened. Well, if their stories don't line up, if they have nothing in common, you know something's wrong. Their stories are inconsistent. As opposed to two children that are telling the truth, their stories would match up, their stories would intersect, their stories would be consistent. That's how I like to remember which one is which. If the lines don't intersect, the system's inconsistent. If they do intersect, it's consistent, and then we ask ourselves, well, how many times do they intersect? Do they intersect just once? If they do, the system is also going to be called independent. It's going to be called a consistent, independent system. Sometimes they're going to intersect more than once. Those lines are going to be called, those systems would be a consistent, dependent system. And this is what it looks like visually. If you look at the graph of a system of equations and it intersects, it's two lines that intersect. They have one solution right here. That's the only spot they intersect, one solution. This is a consistent, independent system. Sometimes the lines will intersect everywhere. Here, 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 all over. These have infinite solutions. And when that happens, this is a consistent, dependent system. The way I remember the difference between those two, dependent and independent, if you're independent, you're just a one-man show. You do everything on your own. One person, one solution, one point of intersection, independent. Versus these lines, the one is literally laying on top of the other line, expecting it to support it up. It's dependent. And then here's an example of when they don't intersect at all, like parallel lines. These have no solution, and we just write it with this symbol. Here's the same information taken right from your book. A system that has one solution, intersecting lines, is consistent and independent. If it's the same line on top of itself, consistent and dependent. And if the lines are parallel, they would be inconsistent. It is not possible for an inconsistent system to be dependent. It is not possible for an inconsistent system to be independent. You can't have it. In order to be dependent or independent, they need to at least cross once. All right, let's look at the last way to solve systems of equations using an augmented matrix. We haven't done much work with matrices yet, and we will in the future. We'll get to more in-depth study of matrices in the future steps to come. But right now, we're just going to use what's called an augmented matrix. A matrix you can kind of think of as, these are all matrices by the way, is like an organized little chart or table. And we can take each equation in our system and create a row in our matrix. And then the columns, think about architecture. If you have a column on your front porch or a column in a museum, the columns go from the ground to the top. The columns are vertical, okay? So that's how we can remember that these are the columns going up and down versus the rows that are going side to side. Okay, so each column is going to represent a different variable. And then the final column will represent the constants. So for now, we're not going to worry about a system of 3 equations with 3 variables. We're not going to do that yet. That's going to happen in step 9. Right now, we are only going to use 2 variables. And let's take a look at an example of how we would do this, because sometimes the example helps make the notes make a little bit more sense. So to start, I like to always have my equation, each equation in standard form. That means x's, y's, and a constant. Now, technically this is violating standard form because remember standard form, the coefficient of x is positive. But it's okay, we're going to let it go for right now. We just want to create a matrix. I have 2 equations, so it's going to have 2 rows. This equation will go in the top row. The second equation will go in the bottom row. Now, when I write my equations on these lines, I don't put the x's or the y's. So in my first column right here, these are going to be my x's. My next column is going to be my y's. And my third column is going to be my constants, or the numbers that don't have variables. So we're starting off. The green equation, I want the number, the coefficient of x. So -3, 8, 36. The second equation is going to be 6, 1, -21. So I'm just going to rewrite this without all of the highlighting. -3, 8, 36. 6, 1, -21. This is called a 2 by 3 matrix because it has 2 rows and 3 columns. And you always list the rows first if you're naming the dimensions of your matrix. Now, what are we going to do with this matrix? Well, we're going to use either our graphing calculator or Desmos, and it's going to reduce it for us. It's going to put it in reduced row echelon form. That's the technical word for this. Let's look at what happens when we put this into Desmos. So I'm going to Desmos. Notice I didn't go to Desmos.com graphing. Now I went to Desmos.com/matrix. That's very important. We want to go to the matrix. I also want to be able to see my other screen right now. Okay, I want to see them both at the same time. Here we go. That looks pretty good. All right, this is what we're going to type into Desmos now. So I want a new matrix. Now, this matrix is 2 by 2. Remember, we need ours to be 2 by 3, so I'm going to click plus, and now I have a 2 by 3. I'm going to type -3, tab, 8, tab, 36. You can also just use your mouse and click on it. 6, 1, -21. And I'm going to hit enter. So I have my matrix entered into Desmos. Now I'm going to tell it that I want it in reduced row echelon form. That's RREF. So I click RREF and it says, sure, which matrix do you want me to do that for? Well, we called our matrix A by default. So I say A, and it tells me the answer right here. It tells me that 1, 0, -4, 0, 1, 3. Let's copy that down. 1, 0, -4, 0, 1, 3. Now we've solved this matrix actually. We've solved this system using substitution and elimination already. We knew we were going to get -4, 3 for the answer, but here's how you read it. Looking at the answer. So this is how we set it up and enter it, and then this is going to be the answer. Remember, this is the X column, this is the Y column. So what this literally says is 1x plus no y equals -4. And what this says is no x plus 1y equals 3. So when you have your matrix in reduced row echelon form, you'll have 1s on the diagonal here, and then you'll have your answer next to it. Looking at the example in our notes up here, you'll see the same thing happen here. We have 1s on the diagonal. Again, we're not going to focus on 3 by 3 just yet. We'll do that later on. And our answer is to the right. Sometimes, though, when you try to reduce it, you'll get something like this, where you don't have 1s on the diagonal and you have a whole row of 0s. When that happens, you end up with infinitely many solutions. Other times, if you look at a row and you have 0 and a 5, think about what that says. That says 0x plus 0y equals 5. Is that true? No. That is not true. That is false. Up here, we can have 0 equals 0. That's okay. That's true. Infinite solutions. But when we get no, that's false. No solution. So let's try to take a few more examples. We will put them into the matrix calculator and see what we get for an answer. So for this first one, when I write the matrix to set it up, I have a little bit of problem first, right? I can't really go right into putting my numbers. I don't want to just go 1, -1, -9, 3, 5, 5, because this is my X column. These are not X's. Furthermore, this is supposed to be my Y column. These are not Y's. And here are my numbers. They might be okay, but bottom line, we can't just start dumping the numbers into the matrix without getting it into the right form first. So I'm going to add X to both sides so that I have X plus Y equals -9. And then I'm going to subtract 5X from both sides of the second equation, plus 3Y equals 5. Now I can take and put it into a matrix. 1, 1, -9, -5, 3, 5. And running this through the matrix calculator, again, I can actually just go right up to the one I had already typed because it has the same dimensions and just change what's written. 1, 1, -9, -5, 3, 5. And you can see the answers just show up right down here. The solution to this system is 1, 0, -4, 0, 1, -5, which means my answer is -4, -5. It's much faster than substitution or elimination. All right, how about A? Let's go ahead and write a matrix for A. Example A, 2, 3, 5, X, Y, number. And when we type it in to Desmos, 2, 3, 5, 6, 9, 15. What happened? Well, the answer, we have 1, 1.5, 2.5, so we already know something's up because usually this is a 0. And the next line we have 0, 0, 0, which is true. But our answer isn't 2.50 because there is not a 1 right here and a 0 right here. It has to be in that form to get one solution. This is an example of where we have infinite solutions. Go ahead and pause your video and try B and C and see what you get for those answers. Hopefully for both B and C you got no solution because you have a row of zeros that end in 1 and that means no solution. Let's actually take this concept that we're learning on solving systems and take a real-world example and use what we know with matrices to solve this. A cashier has 25 coins consisting of nickels and dimes with a value of $1.95. How many of each type of coin does she have? Well, first we need to talk about what are the two things we're talking about in this problem. The two things we're talking about that we don't know how many we have are nickels and dimes. Now, you can use X for nickels, Y for dimes, because we don't know how many we have. That's what we're trying to figure out. Personally, I like to use the same letter that the word starts with, so N and D. It works either way. A cashier has 25 coins consisting of nickels and dimes. What does that mean? That means if I take the number of nickels, which I don't know how many there are, by the way, this is number of nickels and number of dimes, and add them to the number of dimes, I would get 25. Then I have this little bit of information, a value of 195. A value of 195. Well, think about how you find the value of the money in your pile. You take how much a nickel is, which is 0.05 cents, and you multiply it by the number of nickels. Then you do the same with dimes. 0.10 for 10 cents times the number of dimes, and you add that up. So you give each nickel 5, 10, 15, 20, and so on, and the dimes 10, 20, 30, 40, 50, all the way up till you get to $1.95. This is our system, which we are now going to put into a matrix. 1, 1, 25, 0.05, 0.10, or just 0.1, and $1.95. Now we'll take and put this into our Desmos matrix calculator. 1, 1, 25, 0.05, 0.1, 1.95. And it tells me that I have 11 nickels and 14 dimes. My answer matrix is 1001 with 11 nickels and 14 dimes. And you can check it. If you take 11 plus 14, do you get 25? Yeah. If you have 11 nickels and $1.40 in dimes, is it $1.95? It sure is. So we know we're right. Typically speaking, when you're coming up with your system, you're going to have one equation here that has to deal with quantity. This is kind of a general rule of thumb, and you'll have an equation that has to deal with value. That's a kind of a safe way to assume to set these up. Now let's see if that applies to our next one. Now we're talking about a theater. There are tickets that are $6 for adults, $4.50 for students, a total of 145 tickets. They want to know how many of each kind did we sell. So again, we have some unknowns. We have adult tickets, which is the number of adult tickets. We don't know. And we also don't know how many children tickets, or actually I'll call it S for students. But I do know that there were a total of 145. Quantity, there were 145. The number of adult tickets and the number of student tickets, if I add them together, I get 145. That's my quantity equation. Now I need to think about my value equation. Here's a value, value, value. I know that if I want to figure out how much money I bring in, I take $6 times the adult ticket plus $4.50 times the student ticket, and all together, the adult money and the student money all together equals $780. Turning this into a matrix, 1, 1, 145. Remember, we have the coefficients of the A's, the coefficients of the X's, and the constants. 6, 450, or 4.5, 780. Taking this into our matrix, let's get an answer. 1, 1, 145, 6, 4.5, 780. You can see that our answer matrix, 1, 0, 85, 0, 1, 60, which means 85 adult tickets and 60 student tickets.